Hello, everyone, and welcome to today's stream. And today is Christmas Day, so happy Christmas to everyone who celebrates it at least. So, yeah, let's get into today's Christmas stream. We are continuing Calculus Volume 1, and to download the book, it's in the video description. So, yeah, this is part of the OpenStax initiative through Rice University. It's in their Creative Commons. I have a physical copy of the book. It's a very nice copy. So I personally like having a physical copy, but download the digital one, and when I get to the questions part, you could actually know whether I'm getting them right or wrong before I do. So, yeah, let's get into it. All right, so we are continuing from where I left off yesterday. We're still in, let's see here. 1.1. Okay. So now we are on page 13, representing functions. Typically, a function is represented using one of the following tools: a table, a graph, a formula. We can identify a function in each form, but we can also use them together. For instance, we can plot on a graph the values from a table or create a table from a formula. Functions described using a table of values arise frequently in real-world applications. Consider the following simple example. We can describe temperature on a given day as a function of time of the day. Suppose we record the temperature every hour for a 48-hour period starting at midnight. We could let our input variable x be the time after midnight, measured in hours, and the output variable y be the temperature x hours after midnight, measured in degrees Fahrenheit. And let's take a look. Okay, so on page 14, it gives us a graph. And basically, I'm not going to reproduce a whole graph, but you can look at it. It basically has hours, temperature, hours from midnight, and then the temperatures. So we have 24 hours, and the temperature fluctuates from 58 degrees at 0 hours after midnight. And then 12 hours in, it's 84 degrees. And then 23 hours after midnight, the last, and we're back to 58. So it oscillates, basically. It basically goes something like this. Basically, that's how you can imagine it. All right. We can see from the table the temperature is a function of time. So over here, this would be hours, and this would be temperature. And so basically, that's how it works. And let me fix hours. Yep. So there we go. Okay. We could see from the table that temperature is a function of time, and temperature decreases, then increases, and decreases again. However, we cannot get a clear picture of the behavior function without graphing it. So, given a function f described by a table, we can provide a visual picture of the function of a graph. Graph and temperatures listed in table 1.1 give us a better idea. So then on page 15, they just graphed it. It looks similar to what I did there, basically. And then from the points plotted on the graph, we can visualize the general shape of the graph. It is often useful to connect the dots in the graph, which is represented the data from the table. So connecting the dots simply means this. You just run a line through them. This should be pretty self-explanatory, but if it's not, that's okay. We're going to do lots and lots of these. And let's keep rolling along. This example, also, we cannot make any definitive conclusion regarding what the temperature was at any time for which the temperature was not recorded, given the number of data points collected and the pattern in these points. It is reasonable to suspect that the temperatures at other times followed a similar pattern. So obviously, like, this could have been a sunny day, right? Or there could have been a warm front that was here. It's quite possible. And also, this tells us nothing about what time of the year it is or what latitude, longitude. So all these factors will, of course, affect the shape of it. But generally speaking, you're going to oscillate. Yeah, generally it's colder at night and warmer during the day, right? Now, sometimes we are not given the values of a function in the table form, rather we are given the values in an explicit formula. Formula arise in many applications. For example, the area of a circle of radius r is given by the formula. So r is the area is going to be of r is equal to pi or r squared. So basically, this formula right here, this is the area of a circle. And if you wanted to know the circumference, it's diameter times pi. So this is area. And this is circumference. Probably misspelled circumference, but let's go with it. So that's going to be, just say C of r equals to 2r times pi. That's the circumference. All right. When an object is thrown upward from the ground with initial velocity of v0 feet per second, its height above the ground from the time it is thrown until it hits the ground is given by the formula. So this is st. Negative 16t squared plus VOT. So this refers to, I don't think it's a kinematic equation, but it's of a similar type. When the P dollars are invested in an account at an annual interest rate R compounded continuously, the amount of money after T years is given by the formula A T is equal to P E R T. Algebraic formulas are important tools to calculate function values, often also represent these functions visually in graph form. Given an algebraic formula for a function f, the graph of f is the set of points x. Here we go. So let's just go to a new page here. So let's see here. So given an algebraic formula for a function f, so function f, the graph of f is a set of points. F is x comma f of x, where x is the domain and this is input, and then this is going to be f of x is the range, which is the output. Okay? So now, if the domain of f consists of an infinite number of values, we cannot list all of them, but because listing some of the inputs and outputs can be very useful, it is often a good way to begin. When creating a table of inputs and outputs, we typically check to determine whether 0 is an input. Those values of x where f of x is equal to 0 are called zeros of a function. So x where f of x is equal to 0 is zeros of a function. For example, zeros of x squared minus 4 are, so where does this give us a 0, right? It's 2 squared, but it's also negative 2, so it's going to be plus minus 2. The zeros determine where the graph of f intersects the x-axis, which gives us more information about the shape of the graph of the function. The graph of a function may never intersect the x-axis, or it may intersect multiple or even infinitely many times. So, in other words, like for instance, you could have like a sine wave, right? It's going to oscillate between -1 and 1. Anyway, another point of interest is the y-intercept, if it exists. The y-intercept is given by 0 or f of 0. When I said okay, I gotta do this. So a sine wave oscillates between 0 and pi over 2. And then this is going to be on the y is 1 and -1, and from 0 and pi over 2. So the next one is going to be times pi over 2. So it's, right. That's, anyway, we'll get to that later. I'll worry about that later when we get to it. I don't want to mislead you guys. I'm just going to keep reading the material. Okay. Any point of interest in the y-intercept, if it exists, on the y-intercept is given by 0, f of 0. Since a function has exactly one output for each input, the graph of a function can have at most one y-intercept. If x equals 0, it is in the domain of a function f. Then f has exactly one y-intercept. If x equals 0, it is not in the domain of f, then y has no y-intercept. Similarly, for any real number c, if c is in the domain of f, there is exactly one output f of c, and the line x equals c intersects the graph of f exactly once. On the other hand, if c is not in the domain of f, then f of c is not defined, and the line x equals c does not intersect the graph of f. This can be summarized in the vertical line test. Okay? The vertical line test. Given a function f, every vertical line that may be drawn intersects the graph of f no more than once. If a vertical line intersects a set of points more than once, the set of points do not represent a function. So it's like this. And we're just going to go here, 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 for example. So we could have vertical line here. That's fine. We have a vertical line here on the 0 where x is equal to 0. And y could be like -1 or whatever. And then over here. So these are all fine. Now, if it was like this, and it was going to go back in on itself. So we have multiple points of intersection here. Points of intersection here. This is y is not equal to f of x. And here y is equal to f of x. Okay. The set of plotted points represents the graph of a function because every vertical line intersects a set of points at most once. And B, the set of vertical, let's see, A, B. And B, the set of plotted points does not represent the graph of a function because some vertical lines intersect this set of points more than once. Okay, so now let us consider this function. F of x, just a second. Okay, sorry. Just my uncle just came back from church. Anyway, so continuing on. All right, so now we have f of x is equal to negative 4x plus 2, and we're going to find all the zeros of f. We're going to say find all zeros of f. Okay, so we're going to do this. We're going to say negative 4x plus 2. We're going to say, where does that equal 0, right? That's what we want to know. Okay, so then we're going to say minus 2, minus 2. So then we have negative 4x is equal to negative 2. And divide that by negative 4, divide that by negative 4. X is equal to 1/2. So at 1/2, the function is going to equal to 0. So, and we can check that by multiplying negative 4 times 1/2 plus 2, which is going to be equal to negative 2 plus 2, which is equal to 0. All right, so we're going to say where x is equal to 1/2, or 0.5. Okay, B, find the y-intercept if there is one. Okay, so then what we have to do, and y-intercept is y is given by our formula. So we're 0, f of 0. So we're going to say where it's 0, f of 0. And where is that? So remember our input, and then we want to know what our output's going to be. So in this case, if we put in 0 into the 4x, so negative 4 times 0 plus 2, that's going to be 2. So it's going to be 0, 2. If we put in 0 in the x, 2 is going to be the output. All right. Okay, now, in the last part, given that sketch a graph of f. All right. Well, let's just do some of these here. So we're going to say x, y. If x equal to 0, y is 2. If x is equal to 1, y is going to be negative 2. And if x is equal to 2, y is going to be negative 6. If x is negative 1, y is 6. And yeah, that's fine. That's enough points for us to graph it. X, y. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so we're just going to say this is 6, this is 6, negative 6, negative 6. All right, and of course the center is 0. All right, so x is 0, y is 2. We're going to mark this here. So that's 0, 2. And x is 1, y is negative 2. So that's going to be 1, negative 2. And x is 2, y is negative 6. So that's 2, negative 6. And x is minus 1, y is 6. So minus 1, 6. And then we can just run a line through them. All right, like that. Okay. And yeah, if you look at it, in the book, they also sketched it. For them, they only did like this part. They zoomed in like to here. And I just did a bigger thing. So that's fine. But it's the same graph, so it doesn't matter. All right. Continuing on, let me just get a sip of coffee here. Using zeros and y-intercepts to sketch a graph. Consider the function. Let me just, I'm going to go back up top a little bit. F of x is equal to square root x plus 3 plus 1. Okay. So we want to know, does this thing break down anywhere? And it does. We cannot, remember what we did yesterday. So if we're going to say x is going to be -3, so that's going to be equal to, we want to know where -3 plus 3 is equal to 0. So, and that is it. We cannot have x be a bigger negative. So x such that x has to be greater than or equal to -3. Any other number's fine, but we cannot go more than, because if it's -4 plus -3, that's going to give us a -1. And because we're in the reals, that's not allowed. We cannot have -1. So, square root -1. So in reals, this is not allowed, square root -1. That's in the imaginaries, and that is like, it's like 1i, but not in the real set. Reals do not allow imaginaries. So, and in general, whenever we think of numbers, just like the colloquial idea of a number is basically the real set. All the numbers that you normally think of, like pi, square root 2, -1, 5 divided by 29, a billion, a trillion, negative quadrillion, all of these are in the real set. And reals range from -infinity to positive infinity. Okay, so here we go. What we do is, and of course, reals also have, they can be infinitesimally small. And, you could subdivide the reals. Like you can keep subdividing it in such a way. There's more numbers between 0 and 1 in the real set than there is in all of the natural numbers, for example. And the natural numbers range from 1 to infinity. Anyway, but that's like set theory. And we're not going to worry about it in this video. So we know that x is limited. It has to be greater than or 3. And then, so what we're going to do is find all the zeros of f. So, where is, hang on a minute here. Now, what we want to know now is where is this 0? To find the 0, this just shows us all the x's we can use. Now find zeros of f. So, to do that, we're going to take our equation, square root x plus 3 plus 1 is equal to 0, and we solve that. -1 minus 1. So that's equal to x plus 3 is equal to -1. And so what we want to do to solve this is, hang on a minute. See, we can't get a -1 though. So since square root of x plus 3 is greater than or equal to 0 for all, there are no solutions. So there are no zeros. Yeah, no zeros. Because we cannot get in the real set right here. So yeah, as I've established earlier, so no zeros. Zeros of f, okay? Now, next thing we want to do is find the y-intercept. So to do the y-intercept is going to be we're going to say 0 f of 0. And to solve that, we're going to input 0 and see what we get, basically. So we're going to say square root 0 plus 3 plus 1. Okay, and that is equal to root 3 plus 1. All right. So our result is going to be 0, root 3 plus 1 for the y-intercept. Now we're going to graph this thing. To graph this function, again, we're going to make our values. Sketch a graph of x. So again, we're going to have x and y. Now what we're going to do is, the other option, when I write x and y, we could also write f of x because that's the output, right? So we are graphing between x and f of x is the y-intercept, basically. So let's do that. So we have our equation. Now, because we have a square root here, we want to pick our numbers carefully. We want to pick them in a way that they're not going to drive us nuts, right? So let's pick a number that we can square root. Let's say x is equal to 1. So then we're going to have root 1 plus 3 plus 1, which is going to be root 4 plus 1, which is equal to 3. All right, see how nice that is? Now, if I went with x equals 0, we're going to have root 3 plus 1, and then you got to calculate that with a calculator, and then it's just going to be imprecise, basically. But just so you know what root 3 is, that's 1.732 and so forth. So that would be like 2.73, so about like 2 3/4, roughly speaking, if we wanted to graph that. Well, since I did it anyway, let's just do that. So that's going to be 0, and that's going to be 2, and that's going to be approximately 2 and 3/4. Okay, that's approximate. We don't necessarily have to hit that mark. We could just pass a line through it. Next, what we have here, I want to use numbers that are convenient for us. We've established that x cannot be less than -3, right? So let's just go with -3, okay? And if we did -3, well, that's going to be 1. So that's y is equal to 1. All right. Yeah. Okay, well, let's see where our graph's given us right now. It's not that many points, but we can probably get some idea of a graph. Okay, so we have 1, 2, 3. This is going to be our -3. 1, 2, 3. 1, 2, 3. That's going to be -3. 1, 2, 3. This is going to be 3. So this right here is going to be y, which is equal to f of x, and this is x. So we have input-output, basically, right? All right, so we have x is 1, f of x is 3, okay? X is 0, y is 2 3/4, so give or take about here. I'm going to say that. It's imprecise, but it's approximate. X is -3, y is going to be 1. Okay. So we can kind of get an idea of what this thing out. We cannot go lower, so the line will not leave, but it will continue upwards here this way. So it's not going to leave the graph here. From here on, how far is it going to go out? We could probably do one more point. So we got f of x. Let's see what other number we can do that's easy to square root. We can do x equal to 6 plus 3, that's root 9, that's 4. Okay, so x is equal to, let's go as x is equal to, wait a minute here, let me think about what other easy. So if we did x plus 1, that gives us 4. Root 6 is not easy, root 7, root 8. Root 9. Yeah, that's about it. So we're going to do a 6. I want whole numbers, basically. So that's 6 plus 3 is 9, plus 1 is 10. So x is equal to 6, y is going to be 10, so that's 3, 4, 5, 6. and that's going to go off the chart 3, 4, 5, 6, 7, 8, 9, 10. So that is that right? Oh, no. That was wrong. And the reason that was wrong is, right, 6 plus 3 root plus 1 is going to be 3 plus 1, which is 4. So it's 4. So if x is 6, 1, 2, 3, 4, 5, 6, this is going to be 4. We're going to be up here. So there we go. This is, notice how it curves, right? This line, and it starts here. It has a beginning. We cannot go lower than x equals -3. So that's our form. It will go on for infinity in terms of how far to the right it can go, but it cannot go any further left. And this way is just going to continue on. Okay, so that was that. Okay. Get another sip of coffee. All right. Example 1.5. Find the height of a free-falling object. If a ball was dropped, so we're going to say 100 feet. And we're going to say this is 0 feet. Okay? It's dropped from 100 feet. I'm going to mark this as 100 feet. All right? Then, for convenience sake, I'm going to move this over. There we go. All right. Okay, so we have 0 feet, we have 100 feet. Okay, a ball is dropped from 100 feet. Its height S. If a ball is dropped from 100 feet, its height S at a time t is given by the function. Okay, height is time t, and we're going to go S of t is equal to -16t squared plus 100. Okay? S is measured in feet, t is seconds. Height, feet, and seconds. Okay? The domain is restricted to the interval, so we are doing, our input is going to be from 0 to c. I believe c is the speed of light here. Where 0 is the ball is dropped t. Oh, sorry. C is the time the ball hits the ground. So 0 is time 0. Time equal to 0. Point of release. And then C is impact ground. Okay? Now, when the ball, here we go. So we're just going to have to start inputting it and getting results. So we take our formula and let's do that. So we're going to say this is t and this is s of t. Okay? So again, input, output. T is 0. So we drop it into the t squared. That gives us 100 back. Okay? All right. T is 1. So that's going to be it's 100 minus 16. All right. So that's going to be 84. Yep. All right. T is going to, what did they want to know exactly here? Okay, 0.5. All right, we're going to do 0.5. Okay, this is a little backwards. It's not, we're not traveling back in time. I know I put it out of order, but it's whatever. As long as the numbers match up, it's not just going to flow back. But, so 0.5 squared. What is that, like 0.25, 2.25 or so? I'm just going to be 0.25. 0.5 times 0.5 is 0.25. So 0.25 times 16 is 4. So that's going to be here 100 minus 4, 96. Okay? And then what other numbers they wanted us? 1.5 times 1.5, 2.25, and multiply that by 16. That's 36. So then we have 100 minus 36. So that's going to be 64. Okay. And then we have 2. So that's going to be 4 times 16, which is 64. That's 36, right? Yep. So it's 100 minus 64, 36. And finally, they wanted 2.5. Okay, so 2.5 times 2.5, 6.25 times 16 is 100. Okay, so that's 100 minus 100, 0. So the impact is at 2.5 seconds. All right. And so now we're going to mark this. So we have feet, and we're going to drop. This is, by the way, the ball itself, it's going to go straight down like this, right? It's falling in a straight line down, presumably. Presumably, we're just releasing it. We're not like throwing it down. We're simply going pop. We're just letting it go off a balcony or whatever. It's just going straight down. But there is acceleration, and this graph is going to show us that acceleration. So keep that in mind. It's not going to be a diagonal line. It's going to have a curve to it. So we're going to go in 0.5s. 0.5, 1, 1.5, 2, 2.5. Okay? So this is our first point. We have 0, 100. The next point is going to, and we should also divide the 100. So let's say this is going to be, this is 50, this is 75, this is 25. Okay, let's do it that way. So we have 100, then we have 84. So that's going to be, let's see here. So this right here is going to be, this is 87.5. So that's, in other words, you took 25, divided it in half, and basically that's roughly where that's going to be here. So, and here's going to be, this is going to be 62.5, and this is 37.5, and this is 12.5. Okay, so it was just like a convenient thing. I divided it in 4, and then I divided each of those in half. I know my numbers are a little weird. I could have done this by tens, I suppose, but you'll get the same idea. So we're 84 at 96 at 0.5. So 96 at 0.5 is going to be like maybe here. We're going to say this is, our input was what, 0.5? 0.5, and this is 96. All right. Our next point is going to be at 1, which is 84, which is a little below here, which is 1 and 84. Okay. Next is going to be here, that was 1. 1.5 is 64, so we're going to be about here, maybe. And this is going to be 1.5 and 64. And then we are going to have 2 is 36. It's about, say, like here. So that's 2 and 36. And 2.5 is 0. So it's going to be 2.5, comma 0. So if we follow our curve, we are going to go like this. So notice that there's acceleration. The ball is in free fall, so it continues to accelerate. It's 9.8 feet per second is the acceleration rate. Okay, so and when you do kinematic equations in university physics, you could actually calculate where would the ball be at a certain drop and so forth, and what would happen where. So yeah, there's all kinds of things that you can do. Anyway, but you get the idea now. Let's continue on. Okay, so we have... Note that for this function, f of x is equal to -4 plus 2 graphed in 1.9. The values of f of x are getting smaller as x is getting larger. A function with this property is said to be decreasing. On the other hand, for the function, for this function, for a different function, the previous one, where it's root x plus 3 plus 1 graphed in 1.10, values of f of x are getting larger as the x is getting larger. Function with this property is said to be increasing. So, what are they telling us here? So, as the values of f of x are getting smaller, as x is getting larger, the function is decreasing. So, and then the opposite, so I guess this is what they're saying here. Here we go. Oh, okay, well, we just look at the definition here. We say that a function f is increasing on the interval if for all x1, x2 contained in I, the interval, f of x, where f of x1 is less than f of x2, where f of x1. So basically, this is what they're trying to tell us. Okay, we're going to say f is increasing vol I if for all x1, x2 members of I. In other words, for all the x's in the interval I, if the function, the output of x of 1 is less than the function of x of 2 when x1 is less than x2. So, in other words, it's like this. I don't know, let's just do like this. So we have our x, y. So if our x is increasing and our y is increasing, then that's what they're saying, is that for this is x, and this is x1, this is x2, and then this is y1, this is y2. Notice that x1 is greater than x2, greater than or equal to y2, and conversely, y1 is greater than or equal to y2. So this is increasing. Okay, increasing on the interval. All right. So, conversely, we say all right, where when x is greater than, wait a minute here, if x has to be greater than x2. So the f of x can be greater than or equal to the second one. The y's, the results can be equal, but the x has to be greater than the previous x. X2. Let me fix this. Okay, so x1 has to be bigger than, x2 has to be bigger than x1. The y's can be equal, but generally you could think of it as increasing here, just as I did in my graph. The x1 is less than x2, so the second x is bigger than the first. Kind of makes sense. Numbers are growing of x, and the outputs are also growing. So it's increasing on the interval I. Okay. We say f is strictly increasing onto the interval I if for all x in I contained like this. So yeah, if this thing continues, it's a strictly increasing thing. So each successive iteration, it gets bigger. All right. Now we're gonna say that if we have f of x1 is less than, sorry, f of x2 is when x1 is less than x2. Okay. All right. Now, if we have a function like this, f of x1 is greater than or equal to f of x2. So the second result is equal to or smaller than the first if x1 is less than x2. So our x's are continuing to increase, right? So x1, x2, x to the n. But our y's, our outputs, we have f of x1, then we have f of x2, except, let me think here. I probably didn't mark that the way I want it to. It'll be like this. F of x2 and f of x1. So f of x1 starts here. x1 input, and then our output is up here somewhere. Let's say that to start. And then when we go to x2, we go down here. So notice that our numbers of x, our inputs went from, say, like x1 could be like 1 or it could be 5. But the subsequent x2 is higher. Let's say it's 6 or 7 or 20, whatever. But our output is continuing to drop, even though we're increasing the x. So this is decreasing on the interval. Okay. All right, and here they have a couple more examples. So this is going to be increasing, obviously, as our x's increase. Our line continues here. This one here, notice that it's going to be equal or less with each subsequent. Even as our x's grow, our outputs are going to be less than or equal to the previous iteration of outputs. So this is decreasing. Okay. And of course, the interval ranges from negative infinity to infinity. And this one also decreases, also from negative infinity to infinity. Okay? All right. And okay. Now we have reviewed the basic characteristics of functions. We can see what happens to these properties when we combine functions in different ways using basic mathematical operations to create new functions. For example, if the cost for a company to manufacture X items is described by the function C of x. The revenue created by the sale of x items is described by the function R of x. Then the profit on the manufacture and sale of items is defined of P is equal to x, which is equal to Rx minus C of x. In other words, let's see here, what is R of x is the sale. So basically, yeah, I'm going to write all this stuff out in a minute here. Okay, where are we at? Okay, yeah, we still have some time. Okay. All right, and this is okay. Let me think here. All right. All right, what I'm going to do is I'm going to pause it here, and then a bit later I'll stream continuing from the combining functions, because that's kind of a new idea. And I'm going to try and keep each of these, because these chapters, they go on for like 40 pages. I try to figure out ways to effectively break them up so that the material can be absorbed effectively. So yeah, I'm going to take a break here, and then in the next stream, we will continue on page 20 with combining functions. And all right, I will see you in the next stream.